And we had said that that particular form was only for adiabatic CSTRs. And generally for all those other assumptions that we have on our energy balances still hold, so no shaft work inside there, which we don't really bring up, so I don't make an explicit note of it over there, but also for a single reaction. How do you know it's for a single reaction? Because we're dealing with an X. If we write equations in terms of X's, those are almost always for single reactions. So we had said that that was for an adiabatic CSTR. The interesting part, which we don't really have enough time to go through, is if you look at any of the other flow reactors, so either the packed bed reactor or the plug flow reactor. So I'm going to write these in terms of the plug flow reactor, so in terms of volume. We always ended up with two equations to solve. We had a material balance, which would give us some form of x as a function of v. So that was our material balance. And we also had an energy balance that was dt dv. So we're not going to fill in all the stuff on the right. Nothing has changed here from everything else that we had prior. The tricky part, the one that we don't have enough time to go over all of the math. In fact, I think the only reason that your book goes over it is in an appendix. I think I have a posting from last quarter that went over this math, but I checked the access statistics on it on TritonEd, and not a single person ever looked at that derivation. So that's okay. You don't have to look at the derivation. I'm going to do the math for you right now. I know, right? I went to all that work and nobody looked at it. Here's the interesting thing. If those things are adiabatic, you can get that XA has a very familiar form of the sum of theta I CPI T minus Ti0 over minus delta H, which should look really familiar to the one that's right up above it. It's the same thing whether it's a CSTR or it's a plug flow reactor or a packed bed reactor. Again, under a particular set of restrictions, right? It's still adiabatic. Except, oh, phone, we have a winner. Feels good, right? Now we know who's phone. So this would be for an adiabatic plug flow reactor or packed bed reactor. Normally, neither of these would be of particular usefulness on their own, right? On their own, you still have conversion as a function of temperature, but temperature is changing. So why does that help me very much? It doesn't. On its own, that particular expression down there on the bottom isn't going to help you. You can actually rearrange this into another way, and your book will show you both ways of this. Instead of x as a function of t as I've got up there, you could also rearrange it and write t as some function of x. But regardless of which way you solve either one of those, you haven't actually solved the problem, right? You've still got something that's varying as you go down the reactor, and so you'll end up having to solve one of those material balances. One of those equations. If you wrote it x in terms of t, then you have to go back and solve the material balance. If you wrote t in terms of x, then you have to go back and solve the energy balance. So it doesn't seem like that's particularly helpful. The only thing that changes is instead of solving one differential equation numerically, if I didn't use this substitution, I would have to solve two differential equations numerically, but ODE 4.5 doesn't really care, right? It's not particularly difficult to solve those two simultaneously. So the usefulness of this, the reason we haven't really brought it up prior to now, is the usefulness of that is limited. You usually end up having to solve the differential equation anyway. The reason that this can become particularly useful, that expression that we've written in two different places, here and here, is if one more thing is particularly applicable to the reaction that you're interested in for the reactor that you are interested in as well. In order to make the distinction here, I'm going to put a superscript on both of these XAs, and that superscript is going to be the letter EB, letters EB. So this is the conversion of A as calculated by the energy balance, and that's going to be in contrast to another X that we're about to present. So we can use these. We haven't had to use them up until now because they don't really help very much. The reason that they can help is if the following is true, if the following is the case, if the following is true. If your reactor, or series of reactor, maybe put that in plural, get to equilibrium. So that's the key feature that we have, is the reactors have to get to equilibrium, or potentially, if they don't get to equilibrium, maybe they get close to equilibrium. Close enough that the equilibrium condition is somehow relevant to your particular reactor. Now we have an additional requirement. We can use the K, remember our equilibrium K? And we can take that K and write it as a function of conversion of A. We have seen that before. In fact, we spent an awful long time practicing that. This was all the material that we had in week 1. Right? All the different ways that we can come up with relating K to conversion, or K to pressure, or K to not really temperature, mole fractions, extensive reactions, and all of that kind of stuff. So for an example, a classic one that we would have learned, I don't remember how long ago, is under certain conditions, excuse me, the equilibrium K can be equal to the K sub C, which is equal to C sub B over C sub A. So if I say Kc is equal to Cb over Ca, what's the reaction? Just A goes back and forth to B, right? No exponents or anything like that. Along the way, we probably, in maybe one of the homeworks or something, would have written this as Xa over 1 minus Xa. Right? If the feed was like pure A, something like that, we could end up getting an example that looks like this. This is just an example. This is not always the case, right? You would have to solve that in whatever manner that you did in week 1. But this is an example of what I'm talking about how you can move back and forth between Ks and conversions. It's doing stuff like this that we had practiced in week 1. The reason that that can be helpful is because you can rearrange this and solve for the X and get something like X is, if it were this particular example, you could have X is equal to K over 1 plus K. But just keep in mind that those Ks are functions of temperature, right? We have the old Van Hoff equation. If we wanted to know what those Ks happen to be, it's the same old equilibrium K that we dealt with in week 1, so all the same rules apply for it. But the reason that this is helpful is because we now have another way to calculate Xa. We have an Xa based on equilibrium. So if you're not particularly close to equilibrium in your reactor, that's not very helpful. It still establishes an upper bound for your conversion in that reactor, but that particular expression may not be helpful in solving the problem at all. However, if your reactor does get close to equilibrium, now this becomes an expression which we can set equal to one of these x's. So I'm going to denote this x slightly differently. So this is Xa if you were to calculate it based on the condition of equilibrium. So I put the superscript EQ on there. So if your reactor gets very close to equilibrium, or essentially equal to equilibrium, we now have the condition that Xa, as calculated by your energy balance, is going to be the same Xa that you would get if you were to calculate it based on the equilibrium criteria. So remember, the conditions in order to use this particular expression, yes, the conditions to use that expression were that the reactor has to operate adiabatically, and it has to operate near equilibrium. Most of the time, we'll simply assume the stuff coming out of your reactor is at equilibrium. So we'll just keep that equality set to itself. So we can solve that particular expression. So both of those are a function of temperature. The one on the right-hand side, XAEQ, we would get that from rearranging the Van Hoff equation for T somehow, or just solving it for a bunch of different T's. And then the one for the energy balance would come from this particular expression. So you'd have to know heat capacities, what's coming in, enthalpies of reaction, that sort of stuff. When we have an expression like this, we can solve that. It looks like a nonlinear equation. We can solve it the same way that we solved all the previous nonlinear equations for, I think it was the CSTRs, where we were doing that, which is we can plot XA from the energy balance and plot XA from the equilibrium condition. Wherever they intersect, that's our solution, that's our conversion, and that's where our reactor will operate. So for example, if you were to plot XA on the y-axis, remember both of those are a function of T. So we don't know quite where T is yet. So we're going to plot them as a function of T. The equilibrium one, if the reaction is exothermic, tends to look like this. That is one of the better S shapes that I have ever drawn. So this is X if you were to calculate it based on the equilibrium condition. It usually has kind of an S shape like that. Sometimes it's a little sharper, sometimes it's not quite so sharp, depends on where you're looking at it. The other one, the one based on the energy balance, has a particularly simple form. In fact, I think we had mentioned that previously, which is that this form is linear in T. So for example, if the reaction is exothermic, that delta H is going to be negative, and this is just going to be a straight line going up at some particular slope. The slope would be equal to whatever the sum of theta I CPI over delta H happens to be, but it'll just be a straight line moving from left to right on our plot. So I can add another one. So that should be a straight line, and this represents X, the conversion of A, based on the energy balance. The conditions that we've got over here for this one, that point corresponds to the inlet conditions. How do I know that's the inlet conditions? The conversion at that particular point is 0, because nothing has happened. It hasn't gone through any particular reactor. The peak conversion is usually up around 1. I deliberately didn't put that 1 exactly at the blue line. Equilibrium does not always need to get all the way up to 1. So actually, let me move that even higher. It'll usually get pretty close. If it's exothermal and you keep cooling it down, you can get pretty darn close to 100% conversion, but it's not necessary to get all the way up to 100%. The other inlet condition that you have, the slope of that is based on theta I, which is an inlet condition, and the intercept is based on the inlet temperature. How do I know it's based on those things? I'm just looking at this expression. There's a Ti0 sitting here, and there's a theta I sitting over here. If you rearrange those, that's what happens when you have a straight line. And so this intersection point that you have here, this is your outlet. Of whatever reactor you happen to be running. I'm not saying it's the outlet of a plug flow or a packed bed or a CSTR, because this procedure holds regardless of what reactor you're using. Just keep in mind it has to be adiabatic. If you wanted to, you could then plot what the temperature was coming out of the reactor by figuring out what the temperature is anywhere along that yellow line that you have. Nobody really does that. We're only interested in the outlet conditions. That by itself, again, the reason we haven't brought that up prior is because we've already got a way to solve these things. If we just solve the full differential inside something like MATLAB, we would end up with exactly the same solution as what we've got for the intersection between these 2 points. The reason that this can be helpful is if you don't get enough conversion in a single reactor. So for example, if this conversion that we've got here, so this is the actual conversion that you get of A, i.e. the solution of A, the temperature that you have coming out down here this one is the actual outlet temperature of your reactor. Let's say that that XA is not high enough. What can we do in order to increase the overall conversion? We can come up with more reactors. Another option that we can do is called interstage cooling or interstage heating. And that's where this particular diagram becomes helpful. So I'm going to come back to this diagram, but I need to define interstage heating and cooling first. So hold on to that. We're going to come back to it. So what do we mean by interstage heating and cooling? The name, if you know what the word interstage means, or you can guess what the word interstage means, you've probably got a decent idea of what this is going to look like. It means we cool down or heat up the stream after it comes out of one reactor and before it goes into another reactor. So if we have a feed into our first reactor, I'm going to draw these as PFRs because it's easier for me to draw rectangles than it is CSTRs. If it goes into the first PFR, the thing that it would go into after it comes out of that first PFR is a heat exchanger. If you've never seen a heat exchanger drawn before, they're usually drawn as circles with a little lightning bolt through them. The lightning bolt is supposed to represent energy being removed from that heat exchanger or energy being put into that heat exchanger. So we could call this reactor R-1. For whatever reason, we start numbering it 1 instead of 0. We would call this heat exchanger, the first heat exchanger, whichever one it is, so heat exchanger 1. That heat exchanger will generally cool things down. Or if you have an endothermic reaction, it would heat things back up. After it comes out of that heat exchanger, we then pass it into another reactor. Generally, that reactor is operating under exactly the same conditions as whatever the first reactor was. So we just kind of copy-paste our reactor from one place to another. Helps on design cost. A lot easier to design one reactor than it is two. And then we take the outlet of that, run it through another heat exchanger. And then take the outlet of that, run it through another reactor. And we just keep going as long as we want. So we would call the second reactor, reactor 2. The second heat exchanger 2. And the third reactor, R3. You can have more heat exchangers, you can have more reactors, et cetera, et cetera. How do I figure out? We already know how to size the reactors, right? This whole class has been, how do we figure out how big the reactors are supposed to be? In order to figure out how big the heat exchangers have to be, you'll have to wait till 101B. That will teach you how to size a reactor. So how to size a heat exchanger. In terms of heat exchangers in this class, we're just going to set them in such a way that we know what the outlet temperature is. We don't really care what the size of that heat exchanger is or what fluid it works with. We're going to simplify them to the point where all we know is what's the outlet temperature of those heat exchangers. So what does this process look like if we wanted to add it onto that previous chart that we have? If we're going to add it to the previous chart, we're going to have to deal with that overall conversion again. So just keep in mind the same as we had before. Have I used? No, I haven't used green yet. The overall conversion that we're interested in is going to be relative to the first and the last streams. So the only thing we're interested in here is XA overall. How does XA overall change as you move from this point further down in our chain of reactors and heat exchangers until you finally get to the last one? We're not particularly interested in the individual conversion inside each reactor. If you want to know the individual conversion of each reactor, you'll have to go back and solve the whole reactor. We're just interested in the overall conversion as we move from one side to the other. If we want to figure that out based on that plot that we had before, it's surprisingly simple. If we set, for example, the temperature here equal to Ti0, right, as our inlet temperature, and let's just arbitrarily set the outlet of all of our heat exchangers to exactly the same temperature. So if we wanted to know the temperature here, it would also be Ti0. So it heated up in the first plug flow reactor, then our heat exchanger cooled it back down to where it used to be at TI0. Goes through reactor 2, heats back up because it's reacting. Then we send it through heat exchanger 2 and cool it back down to its inlet temperature. It doesn't have to be back down to the inlet temperature. That's just a convenient scale for us to use. It could be any temperature that we want, as long as we know what the temperature is. If we have a system like this, we can plot it on the previous curve by doing a kind of a stage stepping operation. So remember, our inlet temperature is right here. So this is TI0. There's never any conversion inside a heat exchanger. If you have conversion inside a heat exchanger, you have a real problem. Somebody's probably going to end up losing a lot of money because your heat exchanger is going to get destroyed. Heat exchangers are not supposed to have reactions occurring inside them. So if we think about which direction we would move on this plot, the conversion doesn't change. The only thing that changes as you go through a heat exchanger is temperature. So that represents on this plot a horizontal line. The conversion doesn't change, but the temperature does. We started off at TI0. We reacted until we got up to T, the first exit temperature, and then we cooled that temperature down. So we're going to start walking to the left until we get back to TI0. So I'm going to draw a dashed line. Why did we get back to TI0? That was an arbitrary thing that we had said on this drawing. We said we just need to know what the temperature is coming out of the heat exchanger. If it weren't TI0, you would just either stop that line at whatever temperature it came out at or extend that line over to whatever temperature it came out at. It does not have to stop at TI0. It's just convenient when we're drawing this to have it stop at TI0. Then it goes through another reactor. If it goes through another reactor, it's going to move up in this particular direction until it again intersects here. The nice thing about that particular process is because we're only basing all of this on the inlet to the entire system, right? We're only worried about overall conversion. These two lines, the yellow lines, have the same slope. So this yellow line and that yellow line both have the same slope. The equation for the energy balance has not changed at all. The only difference is now the stuff coming in has a little bit of material reacted with it. So there's our second reactor. If we now go through the second heat exchanger, that's going to cool it down again and move our curve over this way. Remember, we've arbitrarily set it to cool down to the inlet temperature, so that point will be directly above the inlet temperature. And then we're going to react it again because we had a third reactor. So this line's going to come up in this particular direction, and now we're going to be here. So notice we have considerably improved our conversion from this old one to this one by using more reactors. But we've used them in such a way that we cool it down before we get out of, or before we go into the next reactor. The reason that we have to cool it down is because if you just let the thing keep running in a single giant reactor, you're just going to get closer and closer to that same equilibrium conversion. If you want to improve the overall conversion, you've got to cool it back down before you send it through another reactor. All of these steps, you don't have to do them graphically. You can solve all the differential equations and then plot them and get something like this. If you want to prove to yourself that something like this actually occurs, it's just a little bit quicker to do it in a graphical way like this to decide, for instance, how many reactors do I need. This is quite a bit easier than going through and solving all those differential equations because all you need to know is the slope and the equilibrium curve. So those calculations tend to be a little bit faster. That last line, by the way, also has the same slope. Yeah?
If you had enough heat exchangers and TFRs, would this just approach the isothermal case?
You would approach the equilibrium case at your inlet temperature. So for example, let's say all of your heat exchangers always cooled it back down to the original temperature, the feed temperature. You can kind of see from this stair-stepping process that if I were to keep cooling this down, I would come here, go up, here, up, that sort of thing. And I would just step right into the equilibrium conversion above my inlet temperature, which should seem physically realizable or physically reasonable because if my inlet temperature was TI0, I can't do better than equilibrium at the inlet temperature. unless I start taking my heat exchangers and cooling them even below the inlet temperature. And then I can walk even further up the equilibrium curve. So that is an example of what's called interstage heating. If you have, oh yeah, go ahead.
How do you get the reactants to stop reacting in the heat exchanger? Yeah.
Typically, you remove a catalyst. Or if your inlet temperature is below any appreciable reaction rate, you cool it down to a reasonable temperature, something like that. The most common way, though, is take the catalyst out, and that pretty much stops everything. This is the case for an exothermic reaction. If you have an endothermic reaction, you can do exactly the same thing, except instead of cooling it down every time it comes out of a reactor, you heat it back up before it goes into another reactor. So if your system is endothermic, I'm going to try to mimic that S curve, except it's going to be mirrored. So let's see if I can do that. Not bad. Your endothermic equilibrium conversion will look like this. Kind of another squiggly S shape. And your energy balance, what color is that? Yellow? Will go the opposite direction. So here's your XA based on the energy balance. And if you were to do the stair-stepping operation or the back and forth like this, now your curves would come, for example, over to here, step back up to this particular stage, back to here, up, something like that. So that's if we were to do the same exact procedure, except the system were endothermic. So we've got heat exchangers that are heating things back up after they come out of reactors instead of cooling them back down. We would get a very similar plot, except it's kind of mirrored, flipped somewhere on that x-axis. But the process is the same in terms of calculating things. Do I have any important? No, I think that's it. Yeah.
What were the assumptions again? Like from, like are we assuming we let them react long enough that they go back to equilibrium?
Yes. So that was probably the key assumption in here that we haven't really used before, is that whenever one of these things go through the reactor, when it comes out at this side, everything is at least very close to equilibrium every time it comes out of a reactor. If it doesn't approach equilibrium, we can still do this stage stepping, or not really, yeah, call it stage stepping. The only thing is we take partial steps, right? If we wanted 50% of equilibrium, then we draw that line until it hits 50% of conversion. But more often, these things will get pretty close to equilibrium, so we just step all the way up to the equilibrium curve. The other key assumption was related to the assumptions that we've had before. Things like heat capacities are constant, they're not functions of temperature. Anything you need for an adiabatic reaction would still be here as an assumption. And I don't think we had any others. No shaft work, that was another assumption that we had. So let's take a look at actually I'm going to, let's see, yeah, I'll hand it out in a minute. Let's look at an actual example of how I would do something like this. Or actually, you're going to look at an example. So the handout that I'm going to give, actually is, John, are you on here? John, could you hand these out? I'm going to keep talking since we've got about 15 minutes. So I'll define the problem. John's going to hand out the solution. So what you're going to see on that handout is XA based on the equilibrium condition. For a simplified reaction, A goes back and forth to B. And it's going to have interstage cooling and heating, or in this case, interstage heating. So here's what you're going to determine. Oops. That didn't come out very well. Find the temperature of each stream. As well as XA overall for, again, each stream. If the heat exchangers always cool the outlet to 300 K.
Any more copies, Dr. Hughes?
No, that's all we've got. So you'll have to work together. Really? We've printed the same copies every lecture, and we almost always have a stack of extras, but today we don't. It's very interesting. Here's some additional information. This is not like bonus credit or anything like that, so. The other information that we need is we've got pure A fed. The heat capacity of A is 200 joules per mole per Kelvin. Kind of high, but it could just be a big gas ball. And the enthalpy of reaction, that's not a minus. That was in my notes, it's a dash. The enthalpy of reaction is minus 10 to the 5th joules per mole. And your inlet temperature is the same as everything else. So this looks quite similar to that example that we had before. Here's what I would suggest. So when you start off with a problem like this, there's a homework problem that looks just like this. The first thing you ought to do is figure out what's the equilibrium conversion curve, which is the curve that I have just given you. So I've kind of skipped that particular step. When you have a system like this, the next thing to do is figure out the slope of XA based on the energy balance. So in this case, the slope that I'm talking about is if we take X sub A based on the energy balance. I hope I'm being consistent with my colors. I'm not sure that I am. We'll end up looking like, remember, the sum of theta I CPI T minus TI 0 divided by minus delta H. So what would that look like for our particular system? What is theta A for ours? 1, how about theta B? 0. So up on the numerator, we've got a 1 times the heat capacity of A. The heat capacity of A is 200. And then we don't have any more equations, or sorry, any more species. So we would have T minus TI 0 divided by delta H, or sorry, minus delta H, so that's 10 to the 5th. And if we work through that math, we end up with 0.002 times T minus TI 0. Yes. So 300K for this one. So now we know this is the slope I'm referring to. That's the slope of that line for XA based on the energy balance. If you have to do this and you've got a computer in front of you or something, you can just plot that line as a function of temperature and find out where they intersect. If you're going to do it by hand, which is what you're about to do in the remaining 12 minutes, what I would suggest that you do is try to develop something that goes along the lines of, for every delta T equals something, pick a delta T, it doesn't really matter. You go up a vertical direction of something else. That's simply a way, like how do I plot a line? If I want to know how to plot a line, I know the slope, pick a particular element of delta T. So this is delta T. There is no engineering here. It's simply how do I plot a line. If I know for every, for example, 10 degrees in T, I go up XA by 0.02, no, yeah, 0.02, that can help me plot that, right? Because when I'm plotting it now, I can move over to the right by 10 degrees and up 0.02. Or if you pick something a little bit bigger, let's say you go up 100 degrees, right? For every 100 degrees I go right, I will increase my conversion by 0.2. And so I can use that to start drawing a line somewhere on my plot. But ultimately, you're just trying to figure out what kind of a plot do I have on here and figure out where those intersections are. So that's what we're going to finish with for today. We still have another 10 minutes or so, so that's why you have a handout, is to start working on that. And I can post the solutions for these later on as we go. Also, as we go, I will start to show you some of the answers.